Hello fellas, welcome back. This is the second video on rational functions, and we're going to look at continuing graphing and build upon what we did in the first video. So let's get started. Let's look at guidelines. We talked a little bit about them in the last video, but let's actually put some things in place here. Number one, need to determine the domain of the function. Okay, again, when we have a rational function, we want to find out when the denominator is equal to 0. Okay, and that's going to determine our domain. Okay, we want to simplify the function. See if I can cancel anything off in the numerator and the denominator. We saw an example where we were able to do that once, and one example when we couldn't. And now it's going to tell us if we have any holes or vertical asymptotes. So in our examples the other day, when I had, whoops, let me get rid of that. Let's go to pen here. When I have x squared minus 1 over x plus 1, I could simplify that. X plus 1, x minus 1, all over x minus 1. Okay? Now, x plus 1, sorry. X equals negative 1 is not in my domain. But because I could do this, I could cancel, and that's when I had a hole. Okay? Now, when we had the other function, the other example we did was 1 over x minus 2. Okay? I couldn't cancel this part out. I couldn't cancel that negative x equals 2 out of this. And so in this situation right here, I ended up with a vertical asymptote right there. Okay, in both situations, x equals negative 1 was not in this domain, and x equals 2 was not in this domain, but the result were two different things. The function was discontinuous in both situations. This had a removable, what we call the removable discontinuity, and the other one was non-removable. Okay? All right, so that's a quick review from the last video. If there are any vertical asymptotes, remember we talked about the limit from the left and the right to see what the behavior of the function is as we approach that asymptote. We needed to look at the end behavior, which was basically finding out what the function does as x gets really big, approaches positive and negative infinity. We wanted to determine any y-intercepts. Okay, remember y-intercept is when we set x equal to 0. Okay, and we also want to look at find the zeros. Okay, so set the function equal to 0, and we spend a lot of time finding zeros of functions. So let's continue on. Let's talk more about asymptotes. Okay, of a rational function. If I'm in this form, polynomial on top, polynomial on the bottom, such that we have no common factors. In other words, we can't cancel anything out. So now we're talking about non-removable discontinuities if the denominator is 0. Okay, they have no common factors. Nothing can be simplified here. Okay, we have a vertical asymptote whenever there's going to be a 0 in the denominator. Okay, can't cancel it out. Automatically, we're going to have a vertical asymptote whenever the denominator is 0. What we want to think about is the horizontal asymptotes. We need to compare the degree in the numerator and the denominator. Okay? If the degree in the numerator is less than the degree in the denominator, then we're going to have a horizontal asymptote at y equals 0. Okay? For example, if it was, 3x squared over 3x to the third, this is going to grow much more quickly than that, and it's going to approach 0 as x goes off to plus and minus infinity. Okay? If they're the same degree, we're going to look at the ratio of the leading coefficients to determine what we're going to have. Okay? A sub n over b sub n, when the degree is the same. And then if we have the numerator is greater than the denominator, if the degree in the numerator is greater than the degree in the denominator, we're not going to have any horizontal asymptotes, and the function's just going to go off to infinity. Okay? So if I had something like, 3x to the fourth over x squared plus 2, this term up here grows faster than that one, and so as x gets huge, this is going to go off to positive infinity. Okay, so understanding those is going to be important. Let's do an example. Let's go through it pretty thoroughly here. Here's a graph of the function. Here's a function, a rational function. Let's look at the domain. Again, domain is when the denominator can't be equal to 0. And so it's going to be all real numbers except plus or minus 3. And that should be pretty straightforward. Let's simplify this. See if we can cancel them out. Are we going to have vertical asymptotes or holes here? If I factor the top and bottom, what I should see here is that I can't cancel anything out. Okay, I can't cancel anything out of the numerator or the denominator. And so what that tells me is I'm going to have two vertical asymptotes. Okay, and I'm going to have a vertical asymptote when the denominator is 0. So I'm going to have one at x equals 3 and one at x equals negative 3. Okay, that should make sense to you. We should have two zeros of the function. Okay, and that's when the numerator is equal to 0. So my zeros are going to be when 3x minus 2 is equal to 0, which means that x is equal to 2/3, or when x plus 1 is equal to 0, or x is equal to negative 1. Those should be my two zeros. Okay, and I know my y-intercept when I plug in 0 for x here, I get 2 9s. Okay, so there's some useful information right there. Now, we need to look at what's going to happen at the behavior to the left and right of the vertical asymptotes. So again, this is where we have to take some practice here. And so I want to approach negative 3 from the left. Okay, so if I'm approaching negative 3 from the left, I'm thinking about a number like negative 3.00001. Let's say that's coming in from the left. And if I do that, the top term, the top is going to go to a number that's 22. That's easy. I can plug that in. But the bottom is going to go to a very small positive number, because if I square this number, it's going to become positive, and it's going to be just a little bit bigger than 9. And so that means I'm going to take 22 divided by a really small number. So if I had 22 over 0.000001, let's say, we know that that number is going to get really big, and it's going to approach infinity. Let's come in from the other side. And so coming in from the right here, down here would be negative 2.99999, etc. If I do that, the denominator is now, when I square this number, I'm still going to get positive, but it's going to be a little less than 9. So the denominator is going to be negative. And that means I'm going to take 22 divided by a really small negative number, negative 22 divided by negative 0.00001. I'm going to get bigger and bigger, and I'm going to approach negative infinity. So that's what's going to happen when I approach negative 3. Again, you guys should be walking through this one with me. It's a long example. Let's look at what happens from the left. 3 to left, the numerator will go to 28. Now when I'm coming in from the left, I'm talking about x is equal to 2.9999. Whoa, I'm sorry. Not sure what happened there. So I'll keep going. I get a very small negative number. Again, this number I square is going to close to 9, but 9 is going to be a little bit bigger. And so that's going to approach negative infinity. Okay? Let's come on the other side. If I come in from the right, again, coming in from the right, I'm talking about x is equal to 3.00001. Okay? They're going to be a little bit bigger than 9. I'm going to get a small positive number. I'm going to 28 divided by a small positive number is going to go off to positive infinity. Okay? So that's what happens when I approach my two vertical asymptotes. Let's look at the end behavior. So if I want to take this and I want to head off to positive infinity, note here is where I use my guideline. I have the same degree in the numerator and the denominator. When I have the same degree, I look at the ratio of the coefficients. And the ratio of the coefficients here is going to be 3 over 1, or simply 3. So as x approaches infinity, this function is going to approach a value of 3. So I'm going to have a horizontal asymptote there. If you note, if I look at coming to negative infinity, because these two terms are squared, they're the same, they'll have the same sign, so I'm going to approach 3 from that side as well, as x goes off to negative infinity. Okay? Let's put all the pieces together. Let's see what we have here. Here's my function. My domain was all real numbers except plus or minus 3, as we saw. We had these zeros, which was when the numerator was equal to 0. Here is my y-intercept. I determined that my end behavior produced a horizontal asymptote. Y is equal to 3. I had vertical asymptotes at plus or minus 3. And here's the behavior as I approach those vertical asymptotes from the left and from the right. Okay? And this is all just a summary of what we did. And so if we look at that graph now, here are my vertical asymptotes, 3 and negative 3. Here's my horizontal asymptote. Remember, as I came in from the right, I went off to positive infinity. When I came in from the left, I went to negative infinity. When I came in from the left on this side of negative 3, I went to positive infinity. Came in left, I had negative infinity. Here's my 1, 0. Okay? So again, this is a good example. It's going to take some practice, fellas. Here I'm stepping you through this chapter here. Here are some more examples that you should look at, pay particular attention to. Here's a few more problems to practice. The next video is going to be some more just practice, no new stuff here. But again, it's going to take some practice. We looked at vertical and horizontal asymptotes, looking at what happened, what's the function behavior as I come in from each side of a vertical asymptote. What is the function behavior as x approaches infinity and positive infinity? And always we want to find out what the domain and the zeros are. Okay, so again, that's just a summary of what we did in this video. One more video on this section and then we'll move on. Okay, fellas, have a good day.